Right, let's name some organic molecules. First one here, we have this guy with the weird little piece hanging off the side here. So that looks like it's going to be our functional group. If we go to our table R functional group chart, just kind of scan down, we see a double bonded oxygen as well as an OH on the last carbon in the chain is what is an organic acid. So for organic acids, we're going to name our normal carbon chain. We're going to look at these couple pieces right here. So we see 3 carbons in a row. That tells me I'm going to use the prop prefix. So prop, and they're all single bonds, so it would be propane. But because of this functional group, we have to change the name somehow, and the chart tells us that we end up changing the last couple letters, and actually is the example that's on table R. We change the last couple letters in the name to oic acid. So instead of propane, I'm going to get rid of my E, and I'm going to call this guy right here propanoic acid. So it would be propane if it was just H's around our C's, but that double bonded oxygen right here, as well as the additional OH group down there, that's an organic acid, so we call it propanoic acid. Next example on top right, we've got 4 C's right down the middle of our molecule. That's our main chain, but our extra piece, our functional group, is this guy over here. Here's our I. So because it's just an iodine atom by itself, we look, and the first thing on table R tells us it's a halide. It's an example of these things that have the elements from group 17. So with our 4 carbon chain, that's our main piece. I'm going to call this 1, 2, 3, 4, that's bute. So 4 carbons, all single bonds, would be called butane if it was only hydrogens around them. It's not, because we have this I, we have to change the name. And again, table R tells us that if iodine is present, we add the prefix iodo to the front of the name, so it becomes iodobutane. Iodobutane. Most of these functional groups, we add something to the end of the name. We change the end of the name somehow. With the halides, we just add a prefix to the beginning of the name. So it becomes iodobutane. And where is the iodine? Well, it's located right on the last carbon, the first carbon in line. So because of that, we can add the number and just call it 1 iodobutane. And really, if you left the 1 off, iodobutane is still fine. But to be specific, 1 iodobutane will be the name. Last one down here, I've got a weird looking one. This is the strange one, right? We've got this carbon with a double bonded oxygen, but then there's also a second oxygen kind of stuck in the middle here, and it's connecting 2 chains of carbon molecules. So I'm going to look at table R, and again, kind of scan through. And down near the bottom, I see this thing with carbon with a double bonded oxygen and a second oxygen, and that tells me it's what's called an ester. And that's kind of the weird one. That's the one with the strange names. It's kind of combining a couple different things. So looking at this, I need to identify my carbon chains as always. So I'm going to see a 1, 2, 3, 4, 5 carbon chain over here. The 5th one being the last one that has the double bonded oxygen and the other oxygen. And then also on the other side of that second oxygen, I see a 3 carbon chain. So I'm going to have to actually name both of these things. I'm going to leave my pen as red just because it shows up a little better. And the rule for this is you name this chain over here first, as if it was an alkyl group. So I'm going to name my 3 carbon piece. I'm going to call that propyl. Prop being the 3 carbons. YL because it's just a 3 carbon chain. It's not its own molecule. And then you name the other molecule, the other side of the molecule, say over here. That's kind of on the double bonded oxygen side. And that has 1, 2, 3, 4, 5 carbons. So that would be pent. And the ending for that, as again the table tells for esters, is OH. So it would be pentane since it's all single bonds. But instead of pentane, we call it not pentane. Get rid of that. We call it pentanoate. So for these esters, you name this side of the molecule first, the side that's closer to the single bonded oxygen here. And then you go back and name this side of the molecule over here and add the O8 ending. So we call it propyl for those 3 carbons on the right. And then on the other side, the carbon chain, you include the one that's connected to both oxygens, and we call it pentanoate. Doesn't matter which side the molecule is facing, just identify which way the oxygens are going, and you'll know how to name your molecule. Lesson 4 of chapter 13 of 14, the last video we're going to watch that actually has new material for this stuff, is organic reactions, or as you might call them in the real world, magic. Okay, we've got 7 reaction types to get through of organic reactions. First 2 are right here. And they're very similar. I think probably 2 they're very easy to confuse, which is why they show up on the test a lot. You'll see these included on my list of common readings questions. The first one's called addition, and the second one is substitution. And if you think back to just regular kind of chemical reactions we've seen during the year, it's stuff you really have seen already. Addition is what it sounds like. You're adding two pieces together. So you start out with here a double bonded molecule. So you have a carbon or hydrocarbon chain with either a double or triple bond in the middle. So there's some extra room where you could still add something to this molecule if you want to free up some space by breaking that bond. And that is exactly what happens here. You add a Br2 in this case, but some kind of extra piece, it's usually one of those halides, to this molecule. And to do that, you separate this double bond right here. So instead of having the double bond connecting the carbons, you free those electrons up, which means you can add an extra atom right there, and you could add an extra atom right here. And that's what happens right here, or really on the bottom of the molecule in this direction. So those electrons in the double bond kind of swing out, and you now can add two new bromines. You break that bromine molecule up, and you can add now a bromine to each spot, and that's exactly what you see over here as the product. So it's addition because you're adding these two pieces to each other. You have to start with some kind of double or triple bonded molecule to start, because that means you have some extra room still to spare that you can kind of squeeze those bromine, in this case, pieces into to make this reaction take place. The next one is substitution. It's a little bit differently because here you're starting with only a single bonded molecule. In this case, it's just a methane, but it could be anything that's all single bonds. And because of that, substitution, you have to make some room. There's no room right here. Every single spot is taken up. This is a saturated hydrocarbon. So if we're going to include some of these chlorines right here, we need to kick off one of these guys on the first molecule, which is exactly what you do. It's like a single replacement reaction. You would remove this hydrogen off the molecule, pull it off in order to insert and attach one of these chlorines into its place. And that's what happens here. By the end of the reaction, you have a chlorine put onto the molecule where there used to be an H, and the H has moved off and taken the place of the chlorine in the original molecule. So now you release this HCl over here, and chlorine is on what was your methane to start out. So two very similar reactions, just the one you're adding a piece because you still have some room to spare because of this original double bond, in this case, molecule, and in the substitution, you don't have any room to spare, so you have to remove something first in order to plug something else in. Next two types of reactions we have in the first one up here, these two examples, two hydrocarbon compounds, so in this case CH4 and C2H2, are being reacted each time with some amounts of oxygen to make carbon dioxide and make water. Where do we see hydrocarbons reacting with oxygen? Well, usually you see it when things are burning, so we can call that combustion. And that, as you know, you take some kind of carbon compound, some kind of organic molecule, whether it be coal or oil or natural gas or wood or anything like that, and you're burning it. You need oxygen to make things burn. Flames go out if they don't have oxygen. You know that by now, hopefully. So you're going to take some kind of hydrocarbon compound with oxygen and make carbon dioxide and water. That's where you're going to look for to identify these reactions. Look at your reaction and say, okay, what is going on here? What do I start with? What do I end with? Anytime you see a hydrocarbon and oxygen to start, that's going to be combustion. There's a couple of reaction types we'll see that make carbon dioxide, including this one that we'll get to in a second at the bottom here, but there's only this one type of combustion that starts with the hydrocarbons and oxygen at the beginning. The next type of reaction at the bottom is taking sugar, in this case glucose. That's the only one I would expect you to see because everybody by now hopefully can at least a little bit recognize, be familiar with C6H12O6 from bio and from chemistry anytime we've seen it this year. And you're making ethanol, which is a type of alcohol, and you're releasing carbon dioxide. That's going to be what's called fermentation. So that's things like making wine, making beer. It's how yeast make their own energy for ATP in respiration, if you remember from bio last year. So this is fermentation. You're starting with sugar and you're making alcohol and carbon dioxide. Again, carbon dioxide is a common product. Alcohol really isn't, so just look for the alcohol as a product and that will tell you it's fermentation. You got to start with the sugar to get that. You got to break down the sugar molecules. And this is if you've ever gotten, I give the example here of like apple cider in the fall. You buy the jug of apple cider and you forget it's there for a couple of days, a week, and then you come back and it tastes really weird. That's the fermentation process. Where bacteria or yeast that might be in it, any microorganisms, are using the sugar in the cider to make their own energy, and they're releasing carbon dioxide gas. You'll feel the jug a lot of times gets kind of filled with air, and it feels kind of tough to touch. When you open it, you might hear a little air coming out. I definitely didn't have this happen in college where I took a giant jug of apple cider and maybe threw it out a dorm window. That absolutely did not happen after it had filled up with air, and it definitely didn't explode on contact with the ground. That you should probably never do, ever, ever, ever. Our next two reaction types, in the first one here, we see some molecules reacting and making some new stuff. So let's just actually look at the picture and see what's going on here. On the first molecule over here on the left, I see a hydrocarbon chain, and it's got this little OH group right here. So that tells me it's what? That looks like an alcohol to me. So I'm going to write alcohol right there. And I also see on the next molecule a hydrocarbon chain, and I've got this double bonded O and an OH. So a double bonded O and an OH is an organic acid. So it's an alcohol and an acid and then they react by this little arrow. And what do we have over here on the right? I see a double bonded oxygen, I see an O, and then it's connecting these two carbon chains. So that's going to be an ester. So I've got an alcohol and an acid seem to be reacting to make an ester rather, and releasing water. How do they make the water? Well, we see over here it's the OH and the H, just like in neutralization reactions with acid-base chemistry, and they come together to make the H2O. So because we're making an ester in this case, the type of reaction is called esterification, which is exactly, again, what the name looks like. It looks like ester because you're making esters. It's creating esters by reacting acid and alcohol. So just, again, one of those definitions, if you see here looking at a reaction, you identify it as making an ester, that's esterification. And something to remember about this is that they make really sweet smelling compounds. So very like fruity, flowery kind of smells. Those are ester molecules. So we call it, a lot of times you'll see it referred to as organic neutralization, again, because it's like an acid-base chemistry where you take the acid and the base and react them, you get the H from the acid, the OH from the base. Same thing is happening here. You're taking the H from the alcohol and the OH from the acid, and they're going together to make H2O, just like in acid-base chapter. So you get the H2O removed, and it's this neutralization type reaction, but in organic context. So esterification makes esters. Number 6 reaction is nothing really to identify. I don't think I've ever seen an actual picture of this, but it's called saponification, and this is where you're making soap. So how can you remember this? Well, it's right in the name, saponification. So if you look at it, the first couple letters kind of look like soap. It says those 4 letters, S-A-P-O, just out of order. And I know in the past, students who have taken, I forget whatever language it was, they've told me that sapo or sapon in other languages actually do mean soap. So hopefully that helps you remember this. I don't remember ever seeing an actual reaction or diagram like this drawn out for saponification. Usually just will say what kind of reaction makes soap, and it gets right to the point. And that is this, again, saponification. Our last type of organic reaction is maybe the easiest one to remember and look at, identify, because look what's going on here. What do you see in this picture? It's just one molecule right here and another molecule right next to it. It looks pretty similar. And what are they doing? Well, they're coming together and making one longer molecule. You're just combining these things. Same thing at the bottom here. We have one little sugar molecule here, another little sugar molecule here, and based on the arrow, they're now, again, combining, joining into a larger piece. We used the word addition before for different types of reaction, but it's just you're putting these pieces together. So this is called polymerization. It's just making a polymer, making a longer chain from some kind of smaller unit. Think back to bio, all those monomers and polymers you saw last year. So protein, starches, DNA, these are all examples of polymers. If you think of strings of lights at the holidays or a chain, anything like that, a necklace, it's just longer chains, longer stretches of small units that keep repeating each other. So DNA, again, you have the A's and T's and C's and G's, those same kind of units over and over and over and over and over again. That is a polymer, just as proteins and anything else are polymers. So this reaction is just, it'll look like this. You have 2 similar looking units like this, and then you'll have the arrow, and they end up looking like a longer piece. Just you snap them together, you lose some pieces along the way. It looks like you're going to lose some H's there, lose some OH's somewhere, water on the bottom, but you're making just longer chains out of smaller repeating subunits. That's what polymerization is. This really isn't related to organic chemistry in the slightest, and it doesn't really fit anywhere else. I just think it's one of the best chemistry cats anyone's ever done. I didn't want to get through this year without showing it to you, so oh well. That's it. We're done with this, and now we get to start the super fun task of reviewing everything we've done for the last couple months.